Good morning, dear students. Today I am bringing forward stunning, never seen before visuals from the chapter Magnetic Field. If you watch this video from start to end, you will never ever forget these concepts. The video focuses on force, velocity, direction of charged particle in magnetic field and also the path of a charged particle in magnetic field. My students requested me to make this video as the visuals help them a lot and they also have the magnetic field exam in the coming 2 days. First, let us take a look at the direction of force on a moving positive charge. This is a positive charge, this is its velocity vector and this is the magnetic field vector. Point your right hand in the direction of velocity vector. Curl your fingers in the direction of magnetic field vector. Your thumb points in the direction of force on the positive charge. Also notice this force is perpendicular to the plane containing the magnetic field vector and the velocity vector. Next, let us look at the direction of force on a moving negative charge. This is a negative charge, this is its velocity vector and this is the magnetic field vector. Point your right hand in the direction of its velocity vector. Curl your fingers in the direction of B vector. The force on this negative charge is exactly opposite to the direction shown by the thumb. Next, let us look at the path of the charges when magnetic field vector is parallel to their velocity vector. When the magnetic field vector is parallel to the velocity vector of the charges, the force on the charges is 0 and the charges continue to move with constant velocity. Let us look at the path of a positive charge when the magnetic field is perpendicular to its velocity. In this region, the magnetic field vector points into the plane of the paper. The velocity vector of the positive charge is in this direction. Find the force on this positive charge using the right hand thumb rule. The force acting on this charged particle is QVB and the path of this charged particle is a circle. The radius of the circular path is R, which is equal to mv by qb. Let us now look at the path of the negative charge when the magnetic field is perpendicular to its velocity. So this is a negative charge, this is the direction of its velocity and the magnetic field points into the plane of the paper throughout this region. Find the force on the negative charge using the right hand thumb rule. As this is a negative charge, the force vector points opposite to the direction of the thumb. The path of this charged particle is a circle of radius r equal to mv by qb. Next, let us look at the path of the positive charge when it enters the region of magnetic field. This is a positive charge, its velocity is in this direction and in this region, the green region that you see, the magnetic field points into the plane of the paper. When the charge moves in this region where there is no magnetic field, there is no force on this charge and the charge moves in a straight line. When this charge enters the region of magnetic field, it experiences a force which is perpendicular to its velocity vector. So this light blue color that you're seeing is the velocity vector. The dark blue color is the force vector. Let us now look at the path of a negative charge when it enters a region of magnetic field. This is a negative charge, this is its velocity vector and the magnetic field in this region points into the plane of the paper. The dark red arrow represents the force on the negative charge and the light red arrow represents the velocity vector of the negative charge. Let us look at the path of a positive charge when it enters region of magnetic field as shown below. This is the velocity vector of this charge and the magnetic field in this region points into the plane of the paper. Let us now find the direction of force on this positive charge using right hand thumb rule. The force on the positive charge points in the direction of the thumb and this vector is perpendicular to the velocity vector. Remember once again the light blue color is the velocity vector, the dark blue color is the force vector. Let us say the angle between the velocity vector and this line is theta. The angle that the velocity vector makes with this line when it comes out is theta. The radius of this circular path is mv by qb. This angle is 2 pi minus 2 theta, or this is the deflection in the velocity vector. Let us now look at the path of a negative charge when it enters the region of magnetic field as shown. We find the direction of force on the negative charge using the right hand thumb rule. The dark red arrow represents the force vector and the light red arrow represents its velocity vector. Let us now look at the path of the charge when its velocity vector makes an angle theta with the magnetic field vector. We have a positive charge here. The magnetic field vector is in this direction. The velocity vector has two components, Vx and Vy. This velocity vector is inclined at an angle with the magnetic field vector. Let us now use the right hand thumb rule to find the magnetic force on this positive charge. The magnetic force on the positive charge points along the thumb, which is in this direction. This path that the charge takes is called a helix. The radius of this helical path is capital R, which is equal to mvy by qb. The time period t is the time taken to complete one cycle of the helix, and this time period equal to 2 pi m by qb. Next, the pitch of the helix is the horizontal distance traveled by the particle in one time period. This pitch equals horizontal component of velocity into the time period. Let us have a look at the schematic once again so you are able to visualize the helical path once more. Let us now look at the path of a charged particle when both magnetic field and electric field are present and magnetic field is parallel to the electric field. The electric field vector points in this direction and the magnetic field vector also points in the same direction. The particle is given an initial velocity in the upward direction. The pink vector that you see here is the electric force and the green vector that you see here is the magnetic force. I want you to take some time, think and visualize how the path of this particle will be. I will play the schematic now and check if you have got the correct answer. Let me play the schematic once again. This light blue vectors here are the velocity vector of this charged particle. As there is no force along this direction, this velocity component remains constant. But as there is electric field along this direction, electric force along this direction, this velocity component goes on increasing. The path of this particle is a helix with increasing pitch. Observe this velocity component is going on increasing. Let us now look at the path of the charge when magnetic field is antiparallel to electric field. The magnetic field vector is towards right, the electric field vector is towards left. The light blue arrows represent the velocity vector of this charge. The magenta arrow represents the electric force. The green arrow here represents the magnetic force. I want you to take some time and think how the path of this particle will be. Let me play the schematic and observe how the path will be. Initially, the x component of velocity was positive. As the electric force was acting in this direction, the x component of velocity became 0 and again changed its direction. I'll play the schematic once again and observe the vectors and also how this path of this charged particle is. Let us now look at the path of the charged particle when magnetic field is perpendicular to the electric field. The electric field vector points in the upward direction. The magnetic field vector points out of the plane of the paper. Initially, this charge is at rest. Let us now have a look at the path of this charged particle and also the velocity vector of this charged particle. The path of this charged particle is called a cycloid. The x component of velocity of the charge is given by e by b into 1 minus cos omega t, and the y component of its velocity is given by e by b into sin omega t. So this is the x component of velocity and this is the y component of velocity, and omega is qb by m. The total velocity of the body is 2e by b sin omega t by 2. What I want you to observe here is initially at t equals to 0, the velocity is 0. Then it increases to a maximum and then decreases and again becomes 0. Then it increases and again it becomes 0 and so on. I'll play the schematic once again and you observe this velocity vector. It changes like this. We will now look at the same scenario when electric field vector and the magnetic field vectors are perpendicular. and this charge is initially released from rest. We will now be looking at the forces acting on this charge. This pink vector that you see here is the electric force. As the particle starts moving, I want you to think, how will the direction and magnitude of magnetic force be? Let me now play the schematic and show you how the forces act on this charge. The light blue vector that you're seeing here is the magnetic force. What I wanted you to observe here is the magnetic force is maximum when the velocity of the particle is maximum, and the magnetic force becomes zero when the velocity of the particle becomes zero. And also, this magnetic force is always perpendicular to the direction of velocity of the charged particle. I'll play the schematic once again and observe the direction of electric and the magnetic forces on this charged particle. We are again looking at the same scenario where electric field is perpendicular to magnetic field and the charged particle is released from rest. Let us now look at the resultant force acting on this charged particle, the resultant of electric force and magnetic force. The red vector that you see here represents the resultant force. Let me play the schematic and have a look at it. What I want you to observe is this resultant force has a constant magnitude QE, and with respect to this charge rotates around this with a constant angular velocity omega. Let me play the schematic once again.